Section 4.3 is called the definite integral. Now, over the past few days, we've had a function such as this, maybe some function f of x, and we've wanted to find the area from, maybe we'll start here at A and we'll end here at B. So we wanted to find the area above the axis and below that graph. So we've been looking at that area. And how did we do that? We used a summation. And what did we do? We added up a bunch of rectangles, didn't we? And then we made more and more rectangles, got better and better answers, and then eventually we let the number of rectangles go to infinity and we got the exact answer. Now, when we built our rectangles so that every single rectangle had the same width. Do you have to build it so that every single rectangle has the same width? No, you don't have to. So why did we make it so that every single rectangle had the same width? It makes it a little bit easier. Okay? So, but you don't have to. You could have rectangles of different sizes, but what would you have to have? As you build more and more rectangles, what would have to happen? Not necessarily a different function. What would have to happen to the width of the rectangles? Not necessarily. Think about it. When we built 5 rectangles, we had a width, right? We might have delta x is b minus a over 5. Then what happened when we built 10 rectangles? The width got smaller, didn't it? What happened when we built 100 rectangles? The width got smaller still. So the rectangles do not have to be even sized, but what has to happen is... No, the width doesn't have to be the same. The width has to get smaller. It has to get close to 0. Okay? Now, for convenience purposes, we have and we will continue to always make the rectangles be exactly the same size. But the reality is you don't have to. And so what you're going to see in your book is they're going to define something called a partition. And all a partition means is take A to B and split it up into a bunch of pieces. The pieces do not necessarily have to be the same size. So you might split it up like that. So in this case, I would be building 1, 2, 3, 4, 5, 6, 7, 8, 9 rectangles. But they're not all the same size. And we call this a partition. If I want to get my answer to be more and more accurate, what has to happen? I have to build more and more rectangles. But for example, I can't decide I'm never going to change this rectangle right here. I'm always going to keep that one exactly the same. I'm never going to let that one get smaller. Because my answer isn't going to get more accurate, is it? I'm always going to have this amount of error up here. Okay? So what you're going to see is, in this section, you're going to see area is the limit as, and then they use this symbol. And that symbol is read the norm of the partition P. It looks like absolute values, but it's got 2 bars instead. And all that means is, this is a symbol to say, make more rectangles, but make sure that all of your rectangles are getting smaller. They don't necessarily have to be the same size, but they're all getting smaller. And then they're going to have sum from I equals 1 to n, f of ci, delta xi. Okay, so what does all that stuff mean? What's this f of ci? No, it's f c sub I. It's not times I. Well, remember we had area yesterday. We had a slightly different formula. We had limit as n goes to infinity. The sum from I equals 1 to n. F of what did we have? Delta x I. Delta x. In this case, it was times I. So what was this f delta xi? What did that stand for in terms of the rectangles? That was the height of each rectangle. Assuming that we always use the right-hand side, correct? And what was this? This was the width of each rectangle. Okay, so back here in this formula, what's that symbol? The width of each rectangle, but it's called delta x sub I because all the rectangles are not the same size, are they? We're allowing the rectangles could be different sizes. So this is simply saying the width of each rectangle. And what's this? The height. Except now I just have C sub I. So what does C sub I stand for? A constant within the interval of the rectangle. That can change. Does it always have to be the right-hand point? No. Sometimes, for certain rectangles, you might choose to use the right-hand point. Sometimes you might choose to use the left-hand point. Sometimes you might choose to use one in the middle. But you can use any point that you want within the interval. For convenience, when we've done this, we've always used the right-hand point. So this is the height of each rectangle. Okay, so that limit, the limit as the norm of p goes to 0, the sum from I equals 1 to n of f sub ci, delta xi, this is defined to be the definite integral. And the symbol we use for definite integral looks like this. Which should look like a very familiar symbol. What does that symbol look like? It looks like the antiderivative symbol. The difference is we've got numbers here, a and b. All right? So what is this stuff? What's this dx on the end? No, not really. It has been when we talked about differentials, that's true. It's the change in x, which is, give me another name for change of x in terms of our rectangles. Delta x, which is the width. So this is the width of the rectangles. This f of x is the height of the rectangles. And this integral symbol is a shorter way of writing limit as p goes to 0, sum I equals 1 to n. An integral combines a limit with a summation. And so you might remember recently we were talking about antiderivatives, and I told you when you have an antiderivative, you're always going to have this little dx thing on the end. And I said, I'll tell you why in a little while. And here's the answer. Definite integrals, this dx makes a lot of sense. It's just a symbol for the width of each rectangle. We use the same symbol for integrals as we do antiderivatives. And there's a good reason for that, and that good reason will show up in the very next section, where we will do something called the fundamental theorem of calculus. And the fundamental theorem of calculus will connect integrals with antiderivatives. Integrals and antiderivatives are almost exactly the same thing. They're very, very close, and that's why we use the same symbol for them. Okay? All right, so now, remind me of what that problem was on that worksheet. What was the last problem? F of x was 27 minus x squared. And our interval was 1 to 2. And we wanted to find the exact area? Okay. First thing I would do is I would find delta x. What's delta x? B minus a over n. So that's 2 minus 1 over n. That's going to be 1 over n. But now think about what happens. I start at 1 and I end at 2. When I build my first rectangle, what's the coordinate of that first endpoint right there? 1 point something, okay. True. Write it as a fraction. How far over do I move? 1 over n. So if I start at 1 and I move over 1 over n, then where am I? 1 plus 1 over n. So my first rectangle, the right-hand endpoint, and I'm going to use the right-hand endpoints again. My right-hand endpoint is going to be 1 plus 1 over n. Where's my second rectangle going to end? Nope, you added the wrong one. It would be 1 plus 2 times 1 over n. Because I would start at 1, I would move over 1 over n once, and then I would move over 1 over n again. Where's my third rectangle going to end? 1 plus 3 times 1 over n. Where's rectangle number 57 going to end? 1 plus 57 times 1 over n. Where will rectangle number I end? Where I don't know specifically what the number I is. What's that? 1 plus, so rectangle I has right endpoint of 1 plus I times 1 over n. So what's the penalty for starting at 1? You have that 1 right there. If we started at 0, what would we say if we had started at 0 instead of 1, then what would the right endpoint of each interval be? It would just be I times 1 over n. So if you start at 1, you're going to have 1 plus I times delta x. If you start at negative 3, you're going to have negative 3 plus I delta x. So it's still the f of I delta x, except that only works when you start at 0. When you start at any other number, you're going to have that number plus I delta x. No, it would be harder to use the left-hand rule. Because to use the left-hand rule, I wouldn't have an I right there. What would I have? I minus 1. So not only would I need this 1 plus, I would also need an I minus 1 there, which would add even more confusion.
So, like, the ones wouldn't cancel each other out or anything?
No, unfortunately. Because this one has a fraction that has an n on bottom. That one does not. Okay, so here's our answer. We're going to have the limit as n goes to infinity, the sum from I equals 1 to n, and I need to take this is my x value, I need to take that and plug that into my function to get my heights. So that's going to be 27 minus 1 plus I over n, whole thing squared. So again, that's really the only difference. If we had started at 0, we would simply have I over n squared there. But since we're starting at 1, we have 1 plus I over n. So that's the height of each rectangle. And then I still need to multiply by delta x, the width of each rectangle. Delta x, we decided, was 1 over n. Now what? Well, I want to use the rules eventually, but I'm not quite ready to use the rules. Before I can use the rules, I think I have to FOIL out this binomial right here. I don't think I can leave that way. So this is going to be the limit as n goes to infinity. The sum from I equals 1 to n of 27 minus, when I FOIL that out, I get 1 plus 2I over n plus I squared over n squared. And then that whole thing is still multiplied by 1 over n. Now I think I can use my rules. This is going to be limit as n goes to infinity. I'm going to think of this as being 27 minus 1. 27 minus 1 is 26. So I have to take 26 and add it up over and over again. That's 26 plus 26 plus 26, n times 26n. Minus, I've got the 2 over n, and then I have I. So I got to add 1 plus 2 plus 3 plus 4 all the way up to I. Nope, I'm getting rid of the summation. I'm using my summation formulas now. So that's why I had the 26n there. I took 26 plus 26 plus 26 plus 26, and I added it up n times. All right, so now I've got the 2 over n, and then I've got I. What was my formula for I again? Cn is the formula for 26 plus 26 plus 26 over and over again. The formula for adding up I is n times n plus 1 over 2. Plus, I have 1 over n squared, and now I need my formula for I squared. Over 6. Yes? Oh, where's the minus sign? It's right there. How's that? Absolutely, that one should be minus. Why should that one be minus? Because this negative has to be distributed through. So 27 minus 1 give me the 26. That minus sign goes through. That one's a minus. The minus sign goes through. That one's a minus also. Correct. And then I kind of ran out of room, but this whole thing is still multiplied by 1 over n. I'm going to put it in front because I ran out of room at the end. Now I'm ready to do my limit. So my first term, I've got 26n times 1 over n. As n goes to infinity, what happens to 26n times 1 over n? And you get 26. Minus the second piece. That's 2n squared on top. And what do I have on bottom? 2n squared. Don't forget about this n out here. So I have 2n squared on top, 2n squared on bottom. When n goes to infinity, that limit is 1. Minus. How about the next one? What would I have on top? Not into the fourth. I've got an n plus 1, and a 2n plus 1. 2n cubed. I would have 2n cubed on top, and I would have 6n cubed on bottom. 2n cubed over 6n cubed. As n goes to infinity, that's 1/3. So that's 26 minus 1 minus 1/3. How much is 26 minus 1 minus 1/3? 24 2/3. So the exact area of that function would be 24 2/3. Questions on that? All right, now we'll do some easy ones. The integral from 1 to 3 of x plus 2 dx. If I write that symbol, what am I asking you to find? The area. The area of what? All right, so let's draw ourselves a picture. What this integral means is I draw the function. The function looks roughly like this, where this is the point at x equals 1. Y would be 3. 1 plus 2 is 3. And when I plug in 3, I would have 5. So what I'm asking you to do, when I write that integral, I'm asking you to find that area. How would you find that area? That would work. That's the hard way. Finding the limit of the summation is the hard way. I'm hoping you can have an easier way. No, that's the next section. That would be cheating. And in a minute, I'm going to give you a problem that you could not do by antiderivatives anyway. That would be what Joe said. Use the limit summation thing.
Whatever you're going to teach us.
I'm not going to teach you anything. You're going to do something you already know. What if I were to draw this line right here? You have a rectangle. Do you know how to find area of a rectangle? And you have a triangle. Do you know how to find area of a triangle? That's the easy way. So this integral would be, what's the area of this rectangle? How tall is it?
1. Oh, 3. Sorry.
Its height is 3,
Sorry, 3.
and its width is 2. So that has area 6 plus 1/2. What's the base of the triangle? 2. And what's the height of the triangle?
2.
2 also. So that integral is 8. That's too easy? That's okay? You're okay with that? All right. What's that?
I'm trying to figure out how we would have done it the other way. That was the hard way.
Well, if we were doing it the hard way, we would have to limit as n goes to infinity, the sum from I equals 1 to n, on and on and on, wouldn't we? Would have worked. All right, how about the integral from -2 to 5 of, I don't know, how about 2x minus 1 dx? Again, think of what I'm asking you to find geometrically. What am I asking you to find? Probably. We got to draw a picture. It's the best thing to do. What's the graph of 2x minus 1 look like? It's a line. Looks about like this. When you plug in -2, you get -5. And when you plug in 5, you get 9. All right, so what I'm asking you to find here, when we deal with an integral, we're always talking about bounded by the x-axis. So we actually have two pieces. So we have this portion here. That portion we're going to consider to have negative area. Why would we consider that portion to have negative area?
It's below the x-axis.
Because it's below the axis. And then we'll have this portion, which we will consider to have positive area.
Does it go all the way up in that little triangle that's not changing?
Yes, this -1 goes all the way into that little triangle right there. So I think the best way to find the area here is to just split it into two triangles. The triangle below the axis, the triangle above the axis. All right, so my answer is going to be 1/2. How wide is that first rectangle? How far?
32.
It's wider than 2.
Yeah.
That distance would be 2, right? From there to the axis would be 2. Then I got that. It's 1 right there? I don't think that distance is 1.
It's 2.5.
2.5. And how did you get 2.5?
I guess.
You guessed. Excellent guess.
What should we call it?
Is what? What I need to do is I need to find that point right there. I need to find the x-intercept. In order to find the x-intercept, I plug 0 in for y. Absolutely. I need to know what that point is. If I plug 0 in for y, I have 0 equals 2x minus 1. So x is indeed 1/2. So this length right here is 2.5. So this is going to be 1/2 times 5/2 times, how tall is that rectangle? -5. Very good. We would call that one -5 because it's below the axis.
You can call it -5.
Could I call this -5/2?
Or would you?
Well, either this one or that one has to be negative because this has to come out to be a negative answer because it's below the axis,
But not both of them?
but not both of them. Normally, we would say this one is positive 5/2 because normally we read from left to right, and when we read from left to right, we consider that positive. So there's the area below the axis, and then above the axis, that's going to be 1/2 times. All right, how long is this triangle? 4.5. So that would be 9/2 times, how tall is that rectangle? 9. So it looks like our answer is negative 25 over 4 plus 81 over 4, which is 56 over 4, I think. Which reduces 56 over 4 is the same as 14? 14. So that area would be considered 14. All right, one more of these. Well, two more actually. How about this one? The integral from minus 4 to 4 of the square root of 16 minus x squared dx. Yes, we can. All right, so the question is, weird? No, it's not weird. Isn't it what? If I were to write y equals square root of 16 minus x squared, you could square both sides, right? Y squared is 16 minus x squared. So that's x squared plus y squared equals 16. And what does that look like? It's a circle. Except we only have the positive square root. So what do we have? We only have half a circle. We only have the top half. So what I'm really asking you to do, you have the top half of a circle of radius 4. So that integral simply asks you to find the area of half a circle. How do you find the area of a circle? Pi r squared. Except we only want half of it, right? 1/2 pi r squared. So that's going to be 1/2 times pi times 16, because r is 4. So our answer will be 8 pi. That's one of my very favorite questions to put on a test in Calc 2. And the reason why that's one of my very favorite questions to put on a test in Calc 2, in Calc 2, you will learn a technique for evaluating this integral, something called trigonometric substitution. Trigonometric substitution, quite frankly, is a real pain in the neck. And the reason I like to put this one on the Calc 2 test is students tend to forget, what does integral mean? It's much, much easier to think, this is half a circle. The answer is 8 pi. So students will typically grind through, they'll do the trigonometric substitution. It'll take them a good 8 to 10 minutes to get the answer. And then most of the time they'll get the right answer. They'll get 8 pi. But they worked an awful lot harder than they had to.
You like putting this one on Calc 1 questions?
Yeah, I'm not opposed to putting this on a Calc 1 question either. Not at all. Not a bad Calc 1 question either. All right, last one of these. How about the integral from 0 to, I don't know, anybody got a number they like? 1. Not very daring. Of, let's just go 16 minus x squared dx. What do? Draw a graph. All right, so if I draw myself a graph, what does 16 minus x squared look like? The parabola opens down. Looks like so. We're going from 0 to 1. So we're looking at this area here. And now we have a problem. What's the problem? We do not have a formula for area underneath the parabola. We have formulas for rectangles and triangles and circles and trapezoids.
What about that S-guy's method?
S-guy's method. What's S-guy?
The guy whose name starts with an S. I don't know what it's really weird. It's like Snyder or something. Snyder's theorem or something. Symbols, I don't know.
I'm not familiar with the S guy's rule, whoever the S guy may be. Grace.
Could you use a rectangle and do something with the third line?
Yeah, I could draw a rectangle. Unfortunately, if I draw a rectangle, the little piece I have up here still has a parabola up on top, and I still don't have a formula for finding area under a parabola. Then what do? I don't think I have a choice. I think for this problem I have to do the limit as delta x goes to 0, the sum from I equals 1 to n, f of...
So treat the curved section as...
Our only choice on this problem is to do what we did before. And I did make it nice. I did make it start at 0. So we get to just use f of delta x times I. What if I had started at -2? Then what would we have in there? -2 plus delta x times I. Same thing. Okay? So, on some of these problems, you don't have a choice. On many of the problems in this section, you get nice geometric shapes that you have formulas for. Some problems you don't. And you have no choice. You work it out. All right. Well, I guess we'll do that. What's delta x going to be? 1 over n. b minus a over n is 1 minus 0 over n. That's 1 over n. So the width of each rectangle is 1 over n. And for the height, I'm going to take 1 over n times I and plug it into my formula. So this is going to be the limit. As I don't really want delta x goes to 0 there, which isn't wrong, by the way. But really I want n goes to infinity. That's the symbol we use. This delta x goes to 0, that's correct. That's saying we got to make each rectangle get skinnier and skinnier and skinnier, which is the same as saying we got to build more of them. Sum from I equals 1 to n. I'm going to have 16 minus I over n squared. That's going to be the height of each rectangle. And 1 over n will be the width of each rectangle. That's going to be the limit as n goes to infinity. I can use my summation formulas now. 16n, because I take 16 plus 16 plus 16 over and over again, n times. That one's 16n. Minus, this one's going to have a 1 over n squared. And then I need my formula for I squared. What was my formula for I squared again? Over 6. And then this whole thing still gets multiplied by that 1 over n. There's the 1 over n. Now I do my limit. I have 16n times 1 over n. My power on top is a 1. My power on bottom is a 1. So when n goes to infinity, I'm going to get 16. Minus. On top, I would have 2n cubed. And on bottom, I would have 6n cubed as my highest powers. So 2n cubed over 6n cubed, 1/3. 16 minus 1/3 is 15 and 2/3 would be my answer. Questions on that? Okay, the next thing we have in this section are some theorems about integrals. Number 1 says, if f of x is continuous, then the integral from a to b of f of x dx exists. Once again, what does it mean to be continuous? If you're graphing it, you don't have to lift your pencil. There's no discontinuity points, which means there's no jumps in the graph, there's no holes, there's no asymptotes, none of those things. What do I mean when I say the integral exists? How can integrals not exist? Yeah, you could have issues, couldn't you? Because an integral, in the end, if we go back and look at our definition, it's way back, an integral, after all, is a limit. Do limits always exist? No. Sometimes for a limit, our answer was does not exist. So it is possible for integrals to not exist. Anybody give me an example? If what's divided by 0? F of x? Well, f of x is just a function. It's not being divided by anything. If there were an asymptote in the interval, then the integral would not exist. That's correct. So a simple example would be f of x equals 1 over x. So for example, a simple example would be the integral from -1 to 1 of 1 over x dx does not exist. And what would be wrong with that integral? There's an asymptote at 0. And 0 falls within our range. If I were to give you the integral from 1 to 2 of 1 over x dx, would that be okay? That one would be okay because the discontinuity would not be within our interval. Okay? So there's a simple example of an integral that does not exist. Number 2. If f of x is continuous and non-negative, then the integral from a to b of f of x dx is the area bounded by the graph and the x-axis. So once again, we need f of x to be continuous. We need f of x to be continuous just so that we're guaranteed that the integral does exist. And then I say f of x is non-negative. What does non-negative mean? Positive or 0. Could be 0. Could be 0, could be positive, but it cannot be negative. Then what do I mean when I say the integral is the area bounded by the graph and the axis? It's the exact area. For example, going back a page here, or two. Find the right page. This function here was not non-negative. That's a pretty good triple negative, isn't it? Not non-negative. Okay? So when we found this integral, did we get the area? No, because we took the area of this triangle and we subtracted the area of that triangle because that one was below the axis. So you don't get the total area. You don't get the sum of the areas. Where for this function was non-negative on our interval 1 to 3. When we found the integral, we got exactly the area of that shape. So all we're saying is, as long as the function is above the axis, integrals give area. What if your function is above the axis and below the axis? It gives the difference of the two areas. It'll give the positive area minus what we consider negative area. But it won't give you the total area. What would I have to do if I wanted to find the total area of these two shapes? I could add them, which would mean put a plus in front of here. The easy way to fix that would be to put an absolute value symbol around my function, and then my function would always be positive. Yes? How will this ever be used outside of this class? That's a very good question. Anybody have any thoughts?
Does S impulse?
Physics, impulse. Okay, what else?
I was thinking, like mapping, if you want to find how much the area of the lake that you're looking at.
Okay. If you want to look at the area of a lake, the surface area of the lake.
So it's not, I mean, just a rectangle or a circle. It's squiggly.
Right, it's not a nice regular shape, is it?
Yeah.
What else?
Architect.
Architect. How would an architect use it?
Like if they're making a bridge and they're trying to use arches in it or something, it just like it's curved so you can't find the exact area of each space underneath it, but it's just right.
Exactly. So if you're building something, and you're building a bridge, a suspension bridge that looks something like this with the cables maybe, and then the bridge is here on the axis. How long does that cable need to be? You don't know. We will learn how to do that with integrals. We will learn how to find the length of a curve using integrals. Or maybe you need to paint that area. How much paint do you need? Again, you could find that area using an integral. Yes?
Kind of like off what she said, like if you're like trying to figure out how much room you have or something, and you don't like
Correct. And your first take-home quiz is going to be some examples just like that. In fact, I think one of them is a pond, not a lake, and you have to find the area of the lake. Actually, you have to approximate it. You won't find the exact answer. You will approximate the area of the lake. Pond, water, wet stuff, whatever it is. Okay? In the very near future, we will also learn about something called volumes. What's volume?
It's like area, except you make it
Area with height.
multiply it by the height.
So volume comes with three-dimensional objects, doesn't it? It's the amount of stuff you can put inside an object. For example, we might talk about the volume of my water bottle. How would you find the volume of my water bottle?
Put it in water.
It would be pretty easy to get a pretty accurate estimation of the volume of the water that fits in this water bottle. How come? It's almost perfectly cylindrical, isn't it? But not quite, because if you look at it, it's got little indentions here for making it easier to hold. So that it's not quite a perfect cylinder. So what we will learn in the near future is if you have something like this, we'll learn how to set up an integral to find the volume of this object.
Wouldn't it be easier to jump out of the water into something that is a cylinder? And measure it?
For this problem, I would agree it would be easier to simply fill up the water bottle and then dump it into some sort of measuring cup and figure out the volume. That would be the easiest way to go. However, consider if this was not something designed to hold water, what if it was a solid object? Then
Then you put it in water. Yeah. Do like, what is it, displacement?
If it was the size of a building.
but that won't tell you the volume, will it? What will that tell you?
I thought that was a volume.
No.
How much the water changes?
Yes, and what does that tell you? It doesn't tell you volume.
How do you space place?
It tells you density. That's how Archimedes figured out that the crown did not have as much gold as it was supposed to have. It didn't displace enough water to equal that amount of gold. I don't think it tells you volume.
I thought it was volume because it was milliliters to centimeters cubed.
I'm not sure. Pretty sure it tells you density.
Well, it would count for the volume inside, but also the volume that the actual material takes up as well.
Yeah. Anyway, so there's some things that we will use integrals for in the very near future. All right, some more theorems about integrals. Number 3. I have just about enough time to write these down, and then we'll take a look at how we use them tomorrow. The integral from a to a of f of x dx equals 0. Excellent. Why 0? Can I, if I'm starting and ending at the same spot, can I build any rectangles? No. So my area has to be 0. Okay. Number 4. The integral from a to b of f of x dx equals the integral from a to c of f of x dx plus the integral from c to b of f of x dx, where c is any number in between a and b. That looks fairly complicated, but it's really not. Anybody tell me what that's saying?
You're just dividing it into parts.
Correct.
And then it's the sum of the parts.
So all this is saying is if I have some function, here's my function f of x, and I'm finding the area from here, which is a, to there, which is b, if I pick some number in between and I split this into two areas, this would be the integral from a to c, and this would be the integral from c to b.
It wouldn't make much sense. I mean, you could do it, but when it equals less than or equals, it wouldn't make so much sense to make A equal to C.
True, it would not do any good to make a equal to c, but it would still work.
Yeah.
And the reality is we already used this property.
Just dividing into the
We did it right there. We chose to split this into two triangles. And we already used that property. We found the area of that one, we found the area of that one, and we added them together. All right, rule number 5. Rule number 5. The integral from a to b of some number k times f of x is k times the integral of f of x. What's that rule saying? It's a distributive property, isn't it? Because remember what this integral symbol means. This integral symbol really means we're adding up a whole bunch of stuff. So if I take k and I have it out here, that's fine. But if I move k in, I'm really just distributing it through the summation. That's really a fancy way of writing the distributive property. That's all that is. Number 6. The integral from a to b of f of x plus or minus g of x dx is the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. What's that rule?
Separation, I guess.
You can separate. If you're adding within your integral, you can separate your integral. There's a name for that. Close. Not communicative. That would be talking. But it sounds a lot like communicative. Commutative. Because again, remember this symbol here, this just means a summation. So this says, take f of x plus g of x and add them all up. And this one says, add up all the f of x's, add up all the g of x's, and then add them together at the end. Basically, all you're doing is switching order. Switching order on your summations. That's all that one says. I'm missing a rule. Oh, number 7. The integral from a to b of f of x dx is minus the integral from b to a of f of x dx.
This is going the other way.
That's right. Typically, a is the small number and b is the big number. So typically, we go from left to right. What happens if I choose to go from right to left? It's the same, except it's going to be negative because you're going the opposite direction. That's all that one says. All right, I think that's all of our theorems. Tomorrow we will look at how we use some of these theorems, and then we will start to move on to the fundamental theorem of calculus.